Hello and welcome to Physics Teacher. In this video, I'm doing a review for my grade 12 physics students who have a test on energy and momentum. So we're going to go over some true-false questions, multiple choice, and some problem solving. If you have any questions along the way, let me know in the chat. There we go. I've got the chat open, so let me know in the chat and let's get started. So we're going to start with some true-false questions. So here we have number one. We have two number ones, but they're from different tests. So number one, the maximum work a force can do on an object occurs when the force is parallel to the direction of motion. So work is the dot product between force and displacement. So when you solve that dot product, you get force times displacement times the cos of the angle between them. So cos will range somewhere between -1 and +1. So if you want it to be a maximum, you obviously want it to be +1 or -1. And that occurs when cos is 0 or 180. Okay, so yes, that is true. It is when it's parallel. It's not when it's 90 degrees, it's when it's 0 degrees. So true. Okay, the second question one. If you raise an object, so you take an object up over your head and then you put it down on the table, you do the same work as if you only lifted the object up onto the table. This is true because displacement is a vector. Right? So it's just looking at your change in position based on where you started and where you finished, not everything in between. Okay, so once again, true. Number 4. Momentum is not conserved in collisions with an external net force. This is also true. My physics students are probably freaking out because they're used to me doing so many questions that are false. But this is also true. If you have external forces acting on your system, then momentum is not being conserved there. Okay, let's try some more. So here we have some multiple choice questions. First one, we have a person picks up a 1 kilogram box of macaroni from off the shelf and lowers it down into a shopping cart. The work done on the macaroni by the person. Okay, that is extremely important right there. By the person. Oh, there we go. By the person. Notice in here we have, 0. It's not 0, so let's just cross that off right now. But our other two options have both a positive and a negative part to them, right? And by the person is what's important there. So you're lifting something off the shelf. As you lower it, you are providing an upwards force to counter gravity, but its displacement is down. So your force, the force that you're applying, is opposite to displacement. So you're doing negative work. If this question said by gravity and not by the person, well, gravity is down and its displacement is down. So gravity is doing positive work, but you're doing negative work. So we can immediately cancel out the positive values. So without doing any calculations, we know it's either C or E. But we're going to have to do some calculations now. So the force you have to provide is one that is countering gravity. So the force then is going to equal to mg, where m is 1 kilogram, g is 9.8. So this is 9.8 newtons, right? And our work done is going to be negative, because cos of 180 is -1. And then we have our force, 9.8 newtons, times our displacement, 0.77 meters. And we're going to get negative 7.5. So our answer is going to be E. All right, next, period of vibration of a SHM, that simple harmonic motion oscillator, increases. So the period for a simple harmonic oscillator is 2 pi times the square root of m over k. All right, it also mentions frequency here. We also have this relationship that period is inversely related to the frequency. So basically, if period increases, frequency decreases. It does not increase, so C is not possible. All right, mass is directly related to period. So if mass increases, period increases. But this says the period will increase if perhaps the mass decreases. Like, no, the mass needs to increase. So that's not an option. Which also removes this as an option and this as an option. So we only have one left. But if we look at it, we can see, will the period increase as the spring constant decreases? Yes, that's an inverse relationship. So there's our answer, B. Okay, how's everyone doing? Anyone have any questions so far? Okay, we shall continue. A moving curling stone, A, so we have a curling stone A, collides head-on with a stationary stone B. Both stones are of identical mass, okay. If friction is negligible during this linear, elastic collision. So elastic means not only momentum is conserved, but you have zero loss in kinetic energy. If momentum and kinetic energy are being conserved, and this is a head-on collision, A is going to hit B, A will come to a stop, and B will move off with the same speed that A had initially. That's what's going to happen in an elastic collision. So A says stone A will slow down. Yes, but let's see if there's a better one. After the collision, the momentum of stone B will be less than that of... nope, that's wrong. Both stones will come to rest. No. I mean, eventually, if there's friction, they will, but that's an external net force. So in that case, over the long run, it's not being conserved. After the collision, the kinetic energy of stone B will be less than that of stone A. That's definitely no. Stone A is not moving. After the collision, stone A will have a speed of 0. That's 100% yes. Okay, so even though yes, stone A does slow down, E is the better option. Whenever you're doing multiple choice, look for like that most correct one, the one that just hits it dead on. Or head on, sorry. Haha. Okay. Moving on. Even when you're not in class with me, you get corny jokes. Okay. Number 11 I like. It's fairly simple, but it tricks so many students. So this is about momentum. Momentum is mass times velocity. So you have a car of constant mass. So the mass of the car isn't changing, which is, normal, I think. Doubles its speed while driving up a hill sloped at 45 degrees. The factor by which its momentum changes is not hard, 2. Ignore this. Why? Well, if speed doubles and m is constant, momentum doubles. It's that simple. But I get so many students looking at that 45 degrees and doing weird things like times the cos of 45, times the sine of 45. I've even seen times the tan of 45. I don't know where these things come from, but they try to do something with that 45 degrees. You don't, right? It doesn't matter whether you're going up at an angle and you double your speed, or if you're going horizontally and then you double your speed. If you double your speed, you double your momentum. That's it. So be careful of things like that. Question 14. This one, same type of question, but no tricks involved. An arrow's mass is doubled, so the mass doubles, right? So mass, if we were to rewrite this, so mass doubles, and speed is halved. The momentum changes by a factor. Well, 2 times half is just 1. There you go. It doesn't really change at all. Right? If one doubles and the other is halves, no change. Okay. Any questions so far? All right. Next one. 55-kilogram person carrying a 5-kilogram ball slides along a horizontal frictionless surface, then throws the ball forward. So we have, I don't know what they're on, some sort of cart. That was a terrible looking cart. There we go. Person on a cart holding a ball, having a total mass of 60 kilograms, right? Then throws the ball. So the ball is moving forward, the mass of 5 kilograms. So what's happening to this person with a mass of 55 kilograms? His path will not change. No, he's still most likely going forward. So that's an option. The ball will have a smaller angle from the original path than he will. Why is there an angle? He's throwing it perfectly straight. See? Forward. So that is just weird. His speed does not change. No, that's ridiculous. His speed definitely changes. He speeds up. Nope. If he's throwing it forwards, he's got to slow down. So no. He will most likely stop moving forward. It's a possibility, but they're originally moving at some unknown speed v. If this person were to stop moving, then we have a ball of 5 kilograms, which is 12 times the original combination of their masses, which would mean it would need to be moving 12 times that original velocity. So even if you were moving at originally together 5 kilometers per hour, in order to come to a stop, you would need to throw a 5-kilogram ball forward at 60 kilometers per hour. Most likely, no, most unlikely, I think would be the answer in that case. And so I'm going to go with A. Its path will not change. Because to go backwards, you'd have to even throw it faster. I just don't see that happening. So we're going to stick with A for that one. Okay. All right, I think we've tried enough multiple choice questions. I've picked out 3 problems that I like from different tests. One of them could be from the test my students are writing tomorrow. I don't know. We'll see how lucky they are. But I like these problems because I always see common mistakes on these problems. So these are the ones I want to go over. The first one, we have a 1.2 kilogram block is dropped from 48 centimeters above a spring in equilibrium. Okay, so we got a block. Let's call it mass M. It's dropped. So initially speed of 0, and it's going to land on some spring. Okay, let's just call that our spring. Okay, 48 centimeters. So this is 48 centimeters or 0.48 meters. Okay. Then it gets compressed. I don't know what it gets compressed to, maybe to about here. So it goes down some distance x, which is our compression in the spring. That's what we're looking for, that maximum compression. Right? Once it reaches maximum compression, its speed is 0. Okay, now here's what students mess up on. This is an energy conservation question, so ET equals ET prime. And if we look originally, the only energy you have, it's not moving, there's no compression, any springs, so the only energies you have are gravitational. And afterwards, right, it comes to a complete stop. You only have compression in the spring, so the only energies you have here are elastic. The problem comes when students plug in the equation for gravitational energy. Now it's mgh, yes, but what is h? A lot of students like to say h equals 0 right here at the platform. So they say h is 48 centimeters. But that's not true because the block then drops below that amount. So that would mean in the final energy, you should have some sort of negative gravitational. You should always make the lowest point, the object you're concerned with, to be h equals 0. So this right here should be our h equals 0, which would mean h is actually 0.48 meters plus whatever that compression in the spring is. And that's going to be equal to our equation for elastic energy, elastic potential energy, kx squared. So this is the equation that we get that we have to solve for. We can't avoid it. It's going to be a quadratic. You see, you have an x squared term, we're going to have an x term, and we're going to have a term without x. So this involves a little bit of math. Okay, you're going to distribute your mg. So you're going to have 0.48 meters times mg plus mgx is equal to 1/2 kx squared. You can rearrange this now. So if you like, you can have 1/2 kx squared, bring the other terms over, make them negative. So minus mgx minus 0.48 meters times mg, which equals 0. So now, if you didn't see your quadratic before, you can see it now. So you're going to plug in your values. And I taught my students how to just plug in a quadratic onto your calculator. So you don't need to memorize the quadratic formula. That calculator option may not be the greatest for math class, but it becomes very useful in physics class when you don't have numbers that work out so well that you can just factor, right? You always have to use the quadratic formula. Some of my students don't have that option on their calculator, so they have to use the quadratic formula. But either way, if you do it, your two answers, one is going to be 0.41 meters. The other one's going to be a negative answer that we don't care about. So the answer is 0.41 meters. Does anyone have any questions with that one? I don't see anything in the chat here. Okay. Moving on then. Number 5. This one seems fairly simple, but I like it because students make a mistake because they forget momentum is a vector. So let's look at this one. So we have a blazing spike of a 0.290 kilogram volleyball is blocked at the net. It's originally traveling at 18.3 meters per second and bounces straight back. So there's no negative in here for either velocities. This is the clue. It bounces straight back. So it's going in opposite direction than it originally was. Okay, so one of them has to be negative. Okay, after being in contact with the blocker's arm for a total of 18.2 milliseconds. Okay, milliseconds. Okay, so that's 18.2 times 10 to the minus 3 seconds. That's important too. What average force did the blocker exert on the ball? So this is a question where impulse equals change in momentum. So impulse is your average force that acts over some time period, which equals change in momentum, which is mass, times our change in velocity. So if we solve for average force, we get mass times change in velocity, so final minus initial, all over our time. So far, so good, but we have to make sure we plug things in correctly. So what I'm going to do is the positive direction, I'm going to make the direction of where the force is applied, like where the volleyball player is actually hitting. So that would mean that the original velocity, this one, is going to be negative because that was coming towards the person. You can make whatever direction positive that you want. So that would mean what we have here is mass, which is 0.290 kilograms, times that final velocity, that's after I hit it, so that's in my positive direction. So 14.9 meters per second. Subtract your initial velocity, which will be negative 18.3 meters per second. And divide that all by your time, 18.2 times 10 to the minus 3 seconds. And when we do that, we get an average force of 529 newtons. Just check the chat here. Oh, I lost access to the chat. Well, I hope nobody has any questions. I don't know why the chat. Okay. Well, hopefully there's no questions. I don't know why I lost the chat. Okay. We only got one more problem to do anyways. So I'll get through this. If you have questions, you can add them in the comments and I'll look after I've posted the video. And I'll try to answer them if they're there. This one's harder. That's probably why I like it. So we have a 34-gram bullet traveling at 120 meters per second, embeds itself in a wooden block on a smooth surface. The block then slides toward a spring and collides with it. So let's kind of draw what's happening here. So we have, that's our bullet. Okay, I'm going to call it 1. And there's a block over here. I'll call the block 2. Initially, the block is at rest, but the bullet is moving with some speed, 120 meters per second. I'll call that V1. Then it gets embedded into the block. So then we have our block with the bullet inside of it moving together. So 1 and 2 moving together at some speed that I'll just call V2. Then it hits a spring. And of course, that spring gets compressed a certain amount x. So we have the spring constant here. And we know how much it gets compressed by, 12 centimeters. What we want to figure out is the mass of that block of wood. So 2 things are happening here. In this first one, we have a collision, specifically a completely inelastic collision because they get embedded. So we're going to have momentum conservation. And then we have kinetic energy all being converted to elastic energy. So we have energy conservation. Okay. So with momentum conservation, we initially have just the bullet moving. The block is not moving at all, so it has no momentum. So, and I'll make that forward direction our positive direction. So we just have M1 V1, and that's going to equal, afterwards, they're moving together. So we're going to have the total mass. I'm just going to write M total, right? Where M total, just write M total is M1 plus M2 times that V2 that they're moving together, V2. Okay. Over here with energy conservation, although physics conventions are lots of fun, we're doing conservation. Okay, so total energy, initially all kinetic. Okay, and it's both of them together. They're stuck together. So we have 1/2 total mass times that V2, it's this velocity here, squared. Then it gets compressed. That maximum compression is going to occur when it comes to a stop. So there's no more kinetic energy. All you have is elastic energy, which is 1/2 kx squared. The 1/2s can cancel. But you'll notice here we have 2 equations, this one and this one, with 2 unknowns, mass 2 and velocity 2. Now we don't care about velocity 2. Okay? We care about mass 2. So since I don't care about velocity 2, I'm going to take this first equation and rearrange it for velocity 2. If I don't care about it, why am I solving for it? Because I'm going to substitute it into the second equation and eliminate it. So V2 is M1 V1 over that total MT. So if I take that and I substitute it in here, we get mass total times m1v1 over mt, and we have to square that, which equals kx squared. So when we square it, we have to square everything. So let me just do that here. I'm going to remove it from here, and I'm going to square everything inside of that bracket. One of the mass totals will cancel out here, and I can then solve, right? Just rearranging, cross multiplying really. So mass total will equal m1 squared v1 squared all over kx squared. And mass total, like I wrote before, is m1 plus m2. Okay, everyone following? We're almost done. So all we need to do is solve for m2. To do that, I'll just subtract m1 from both sides. I'm running out of room, so I'll write over here. So we get m2 equals m1 squared v1 squared all over kx squared, and then subtract that m1. Everything here we know. You could try plugging those into your calculator, and since we have two significant digits here, two significant digits here, two here, rounding to two significant digits gives us a mass of 12 kilograms. Okay. I hope that was helpful, practicing some problems. If you have any questions, let me know in the comments. Let me just check the chat. No, I still lost the chat for some reason. I'll figure that out for the next time. All right. Good luck, everyone, and have a good evening.